That's right. All right, so we have covered all kinds of spectroscopy. We're finally at the end, the last one, electronic. We've worked our way up. We started with rotational spectroscopy and the spinning of molecules, okay? Then our brain got a little bigger and we did vibrational spectroscopy, okay? And we had all the different, symmetric and asymmetric stretches and we learned how to dance. And then we did the combination of both, right? Row vibrational spectroscopy. P, Q, and R branches. And it got a little harder, didn't it? Yeah. And now we're doing Rovibronic. Like, what in the heck is that? Well, this is the Iodine Lab. That's the last lab of the course. And then you have a revision exercise. But the Iodine Lab is what we're talking about today. And I'm going to walk you through the whole thing. Okay. It's a classic lab experiment that everybody does in PCHEM. Almost, well, any legitimate school makes every student do this in PCHEM because it's this ultimate row vibronic. It's got rotational levels in it. It's got vibrational levels in it, and you're doing an electronic transition. So you see a jump in electronic. The electron cloud is changing. And so we're going to walk through that. It's what we see in the UV vis. So in the ultraviolet visible region, we're dealing with electronic transition. So this is the electron cloud. If it's visible, it's probably the, you know, it's probably the double bonds, things like that, maybe an extended system, because most molecules will absorb in the UV, but if they absorb in the visible region, they probably a bigger molecule. Maybe it's got some aromatic rings or some zigzaggy CH2s, and I mean not CH2s, but unsaturated conjugated chains. We have double bonds, and you stretch that box out. And what happens when you increase the size of the box? The energy levels drop down, so they come out of the UV and into the visible region. So if you look at, you can go on to Wikipedia or any of the internet and look at dye molecules. You'll see lots of double bonds and larger molecules. So those absorb in the visible region, but what's happening in those absorptions is also vibrational changes. And so if you were to get a high resolution spectrometer under one of these big, fat, broad visible peaks, you would see resolve the vibrational levels. And that's what we're going to assign in iodine. We're going to be able to see those vibrational levels in iodine, and we're going to go through and assign the vibrational quantum number to those. And then we're going to pull out a lot of the spectroscopic constants that you get for the iodine molecule. So that's the last lab, the last full lab of the semester. And so what is Rovibronic? Well, they have the rho for rotational, then they have vib for vibrational, and then it's electronic. And so they just put the ronic on the end. I didn't make this up. This is just the way it turned out to be, and the scientists are funny in that way. This is also a lab that is pulled out of Nibbler's book, Experiments in Physical Chemistry, and Joe Nibbler was my thesis advisor, so it was really kind of cool. I didn't know that. I was in physical chemistry. I decided I think I want to do research in physical chemistry, so I went to 4 or 5 universities to look for graduate schools, and I really just loved his lab. There was lasers going everywhere, and it was super exciting. And then when I got back home at UT, and I'm looking at my textbooks and so on, I see his name on the side of my textbook. I was like, oh my gosh, the guy I was just like trying to join his research lab wrote my book. So that was very cool. It would have been probably more impressive to say I saw the author and wanted to go work for him, but it was actually coincidental. I wanted to work for him and then realized he was the author of my PCHEM book. So then we're going to focus on diatomics again because they're the simplest examples. But the same kind of behavior happens in bigger molecules. You just can't resolve things. So for iodine, like very small molecules, we can resolve the vibrational differences. So this electronic excitation causes all 3 things to change. The electron cloud changes, the vibrations change, and so does the bond length, which causes different rotational constants, and you have different rotational levels. Okay. We can almost never see those rotational levels without a high resolution laser. So we have the ground electronic state, and then we have the excited electronic state. So that's the electronic part of the electronic spectroscopy. And then we have those vibrational wave functions. Now the intensities of these transitions they involve the wave functions. And so have those wave functions overlap, like that transition dipole moment integral. That's going to give us the intensities of those wave functions, of those transitions. And so this Frank Condon principle, that's one of the vocabulary words for us. And it's this idea that the nuclei are way more massive than the electrons. And so the electronic transitions occur way faster than the nuclei can move. So think about it. You've got a molecule that's vibrating like this. And compared to light coming in, it's not moving. So like if it's totally stretched out and a photon of light hits it, then it's going to go straight up from this position right here. See, that's the molecule way stretched out in its bond length. The x-axis is the bond length. And then other molecules in that sample may be completely compressed and really close to each other, and light happens to hit that molecule and causes it to transition. And so notice that those straight above this vertical transition is what we're talking about. So straight above that spot, this molecule could hit the excited state, say right here. And straight above this one, it could go way up here to the top if it was vertical. I'm doing a dash line because I can't draw a straight line on this thing. It would hit way up here. And so it's because the nuclei have no time to move on the scale of the speed of light. Light comes in, it's instantaneous. Electron cloud changes. Now the molecule finds itself at a totally different potential energy surface, totally different bond length, totally different vibrational mode, and so on. So let's take the most probable one, the one with the highest maximum here in the ground wave function, and it comes up and it hits this. Now that molecule finds itself in a very much weaker bond, and it will vibrate between these two spots. So look how much more flexible it is. So down here, the molecule only vibrates this much, so like this, and then it gets excited, and all of a sudden it's doing that, way far out. And so there's massive changes in the molecule when we do electronic excitation. We did that Jablonski diagram. Some of those potential energy surfaces were not even bound. Like it gets excited and then the molecule just falls apart. The atom leaves and we have a bond breakage. So these vertical transitions are similar to that Born-Oppenheimer approximation when we were looking at the molecular Hamiltonian, where you pick the locations of the nuclei like we do in Gaussian, and then we calculate the structure of the electron cloud, and then Gaussian moves the nuclei a little bit, recalculates the electron cloud. That's the Born-Oppenheimer approximation that we were using. This is in spectroscopy. This is the Frank Condon principle that just says transitions occur vertically in this energy level diagram. And so those intensities are related to the vibrational wave function overlaps, and that's what we'll see. Okay, let's look at this quantum assignment of these spectra. So if you can resolve the vibrational spectra, you have all of these different transitions. And so let's focus in on this line right here. This is the assignment of this spectrum. So we're saying that all of these transitions start at the V double prime equals 0. That's this level down here. V double prime equals 0. And again, just like the Rovibronic lab or the carbon monoxide lab, the double primes are the lower state or the initial state, and then the primes are the upper states. And so here we have V double prime equals 0, and then it can go to 0 or 1 or 2 or 3, 4, all of these different transitions up here. And so we will label them, instead of writing V double prime equals 0 over and over and over again, we'll just put a bar across and we'll drop a line down to every little peak, and these are the V primes. You see these little lines are showing the V primes. And so it starts out the 0 to 0 transition, and then the 0 to 1, 0 to 2, 0 to 3, 4, 5. Does everybody understand what this little line thing is? It's called a manifold of peaks. And so we're going to see this in our lab, and you're going to have to understand it to do the lab. So you'll have to understand the way we mark these. Okay. And so these spectral line shapes for each of these peaks are asymmetric, and so this tells us why. So also the electronic energy levels are labeled X here, and in this case we have it labeled A. They start out, X is the ground state, is X. And then they go up from there, A, B, C, D, E, and so on. And then we have, let's say the one that's being shown here is the 0 to 4 transition in vibration. So you see this is the electronic one, X to A, that's electronic. The 0 to 4 is vibrational. And then we have J double prime to J prime. Now you could imagine how many J levels we would have. We have P, Q, and R branches and all of those kinds of things on top of here. But the molecule is pretty heavy. So we have an iodine molecule. Each iodine is 127. So the reduced mass is, 127 divided by 2, so, almost 70. So that's in the denominator. The reduced mass for our carbon monoxide was, 6 or 7, And so the spacing in those lines was 2 times that. So the spacing was about 14 wave numbers, and we could resolve that. Here, the spacing is going to be so small, we're not going to be able to resolve it. And so the P and R branches are going to be very, very close together. Plus, notice that bond length up here is much longer. This is Re prime, and down here is Re double prime. And because the bond length is longer in the excited state, notice these levels are closer together. And so what that causes to happen is this thing called a band head. So if we're scanning along, we don't see any peaks, and then all of a sudden all of these R peaks are on top of each other. And it jumps up and it comes down like that. So that's what's called a band head. And it's a common feature, so we see this right here. So somewhere in the middle here is the actual new 0 that we would solve for. But the R branch over here is folded back over onto the P branch. And so this is called a band head. Kind of like a wave, like the head of a wave, right? It's moving to the left, if you will, or to the left. And so we're just finding that the steepest part of that wave of peaks. And so because we have these asymmetric peaks, they occur because we have different rotational constants in the excited state versus the ground state. And they've done this lab multiple times, assigning it different ways. And so when you pick peaks in the past, you would pick the maximum, right? You would go and find the maximum. But we're not going to do that this time. So we're going to say no on that. Okay? We're going to actually pick this spot right here, where that arrow is. Now, why would we do that? Well, because they've done this experiment twice, or multiple times, but 2 ways. Picking the peak maximum gave good results, but picking the minimum on the short wavelength side gave better results. And it was because that band head was more consistently close to new 0 than the maximum. So that's the justification for picking the minimum on the short wavelength side. So this is our Iodine Lab. This is the potential energy diagram. I told you that the ground state is X and the excited state is B. There's probably another excited state somewhere in here called A, but we're shooting past A and hitting B. So we're hitting the second excited state. So that's why we're going from X to B. And so we have the 2 electronic states there, X and B. And then we have the potential energy surfaces associated with those. And because we have a potential energy surface, we're actually plotting it versus internuclear distance. Now, we can only do that in a diatomic sense because we have one dimension, the bond length, and the energy associated with that bond length. But we get to a bigger molecule like benzene or something like that, this really is a potential energy surface. Really, we call that, what's going on with that? Has it always been blank?
No, no.
Oh, you guys haven't been telling me that. That was weird. Okay, I must have hit something, but I thought you were punking me. So anyway, that was pretty funny. Now, I knew that it wasn't because I could see on the back of my video. But anyway, that's what my thought was. Okay, so we call this a potential energy surface, but it's not a surface, it's a line. But all the ones I've shown you are lines only because we're dealing with diatomics. As soon as we get two bond lengths and maybe an angle, now we have too many variables to plot. So we just call it a surface, and it's some undefined surface that has minima at all of the right bond lengths and angles. Okay, so I know that's hard to conceive, and so that's why we don't show it. So we actually really can't plot it, even for water. We have three structural parameters. We have two bond lengths and an angle. So right there we have three dimensions, and then we got to put energy on top of it. So we have four dimensions. We have energy, which we want to plot on the vertical axis so we can see minima. And then structure-wise, we have two OH bonds and an angle. So we can't really even plot the potential energy surface for water. So we'll stick to diatomics. But if you ever wondered, maybe you were sitting in the back and you're like, why does he keep calling it a surface? It looks like a line. Okay, it's just the terminology. So it's in a diatomic, it's just a line. And so those are the energy surface, if you will, for the bond length. We have one-dimensional thing, a bond length. And so there's minima, where you have the minimum bond length for that electronic state. And so we have a bond length for the ground electronic state. If we change the electron cloud, the bonding's different. And so we have a longer bond for an excited electron cloud. It's holding that molecule together in a weaker fashion. And so the bond length is longer. Okay. And so we have vibrational wave functions for the tight bond, and we have vibrational functions for the weak bond. And so we're going to learn about those. And then on top of that, we have rotational levels, which we can't resolve, so we're going to ignore them. But the only thing that they do give us is those band heads. And so it's because of the rotational levels that we have the band heads, and that's why we pick the peaks the way we do. So these are the vibrational wave functions. And also I'm showing here the 0, 1, and 2. So we're going to have thermal population. So we might have I'm going to make up some numbers here, like a 85% here, and maybe 10% and 5%. Did I add up to 100? Yeah. Of population at room temperature, because for iodine, that vibrational energy is about 200 wave numbers, 214, and the thermal energy we have in the room at room temperature is around 200 wave numbers. So we have enough energy to populate the excited states. So we're not doing just the fundamental transition. We may have the fundamental like electronic transition, but we have some hot bands also. So we'll have some hot bands from the 1 and from the 2 level down here. We have those vibrational energy levels, and then we have the equilibrium bond lengths and the ground and excited electronic states. We have the electronic energy difference, so that's the difference in the minima of these two potential energy surfaces. And in this case, these are the bond energies, the dissociation energies. So in this lab, dE is not the centrifugal distortion constant. dE is the bond dissociation energy. And then we have this difference in the excited atoms. So when this excited electronic state, when the molecule falls apart, it has an excited atom. And so the iodines come apart, and one of the atoms is excited. So it takes some of that excitation energy that it had as a molecule and leaves as an excited atom. And so in the atomic spectral database that we have from NIST, we could find out the energy of that excited atom and the energy of the ground state atoms, and we could know this very well, this atomic excitation energy. And if you read the Nibbler handout that's on Blackboard, that figures in to finding the DEs. Okay, so this UV vis absorption in iodine is going from all of these, fundamental and hot, or the ground state and the hot bands, going up to quite a few levels in the excited electronic state. So if you think about this, take the potential energy surface and turn it sideways. And as we're doing a spectroscopic experiment, let's say we're scanning from the infrared to the visible. So in the infrared, we're down here. The arrows are this long. So we got a monochromator. It's an old style spectrometer. We're just turning the grating, sending different amounts of light through the experiment. So as we turn that grating towards shorter and shorter wavelength, our arrow gets longer and longer. And it keeps getting longer and longer until finally it gets this long and it starts to hit some excited state vibrations in the excited electronic state, and we start to get a peak. And so we would see a peak here, and that's the 0 to 14 transition, and then we keep scanning to shorter wavelengths, and then it's the 0 to 15, and then the 0 to 16. And so as you're going to shorter wavelengths, that excited state number, the V prime, is going up by 1. You hit 14, then 15, then 16, then 17, and so on. So it should be pretty easy to assign. And they're all starting from 0. And then we have the hot bands on top of those, and they're in between. So we might have the 0 to 14, and then we have the 1 to 20, and then the 0 to 15, and then 1 to 21, and then the 0, whatever I'm on, 16, and then the 1 to 22. And so they alternate from 0 to something and then 1 to something. And then we throw in the 2s. And we have a 2 to whatever, and then a 1 to something. And there's a place where all 3 of them overlap. Just a small region, but all 3 are overlapping because the spectrometer doesn't care. It's just scanning wavelengths. And if at this frequency it goes from the hot band of 2 to 15, that's great. And if it's at a different wavelength that goes from 0 to 21, that's great too. And so we end up with this really complicated spectrum. Before we get there, let's look at the transition equation. So this transition that we see in the spectrometer, this is the frequency that's being absorbed, and it has the electronic energy differences, it has the vibrational energy differences, and the rotational energy differences. Now we've done transition equations over and over again. With rotation, it was just the rotational energy differences that we were interested in. For the rho vibration, it was really complicated. We had the vibration and the rotation energy differences, and we came up with P, Q, and R branches, and O and S for Raman. And now we've had the electronic. But it's very simple, actually, because we don't have good resolution, it simplifies to this. We have an electronic difference here. So this T prime minus T is just captured in this one overall electronic energy difference. And then we have the vibrations. And the vibrations we're going to include anharmonicity because we're way up, at least in the excited state, we're way up in levels 15, 16, 17, 18. Remember, the anharmonicity is just a measure of how unequal the levels are. So in a harmonic oscillator, you have a perfect parabola that goes up to infinity, and levels are equally spaced. Okay, N means not, so not harmonic. Anharmonic means they're not equally spaced, so they get smaller and smaller as you go up. And so we would be able to detect that the more energy levels we test. Okay, if we only have down in the ground state 0 to 1 and 1 to 2, we're not going to be able to detect the anharmonicity in the ground electronic state very well because we only have 3 measurements, the 3 levels to measure. But in the excited state, we go from like 15 to 26 or something like that. So we have lots and lots of information about the excited state because we're doing absorption. So this is our anharmonic energy sort of approximation. We just did a sort of a quadratic fit to this to see how unequal they are, and notice it's subtractive. So as we go up in V, we go up a whole unit for the harmonic oscillator, and then we subtract a little bit due to anharmonicity. So that's that correction term that we're going to study. So we get the transition equation in wave numbers, and here we have our full thing. So we have the upper states minus the lower states. So we put the primes on there, and then we subtract the double primes. And so now this is positive, but when we subtract it, it becomes negative. You see that? And this is negative, and so when we subtract it, it becomes positive. So that's the subtraction. That's the difference between the upper state and the lower state in terms of the vibrational levels. And it's on top of this electronic piece. Now, when we select all of our columns and do the peak picking, this is the regression equation. So I've told you this, in your notes just have the numbers, but I went ahead and wrote it out. These are the columns that you will use. So you'll assign the spectrum, the vibrational things, and then you'll make these 4 columns. And when you do the regression on it, you get your coefficients. You get nu e xe double primes, you get nu e double prime, nu e xe prime, and nu e prime, and then the intercept will be the electronic energy difference. So the peak picking is the tedious part. You go through and you do that. I know it's tedious, but it's not hard. It's just tedious. Right? So you work your way through that, and then you set up your columns, and you assign those vibrational levels using the peak picking. You assign the V primes and the V double primes, and then you're able to make these 4 columns using those assignments. And then this is your Y variable, and then the columns are your X variables, your X inputs. So here's the spectrum. Here's this peak picking guide. I mean, put a big star on this page. This is the key to your lab. Okay, this is how you get started. So this is the absorption spectrum of iodine. It doesn't go all the way to 400 nanometers, because when collecting this spectrum, we would go and sit in the lab in 302, set up the iodine sample, and it would take like 40 minutes to get this spectrum because it's going really slowly. And so it's a scanning spectrometer, narrow slits, not a lot of light hitting the detector. And so we had to look for a long time to kind of average the signal that we're getting. And then we move the monochromator just a little bit and average again. And so otherwise your iodine spectrum just looks like this. It's just a nice smooth curve like that. Okay. But we sat there for a long time so that we could get the vibrational peaks. So this data is on Blackboard. I know you want to be in the lab, but we would just be sitting there for 40 minutes and get the same data points. So we can just, in our minds, think, okay, I sat there for 40 minutes and got this spectrum, and then you can go download it, okay? So, but that's what happened. Now, it's absorbing the green light. Remember 532, the green laser, the neodymium mag laser doubled? It's 532, so that's green. It's absorbing the green and letting the blue through and letting the red through. So iodine looks purple when you see the gas of iodine. And so it's a purple gas because it's absorbing the green and letting the red and the blue through. But if we zoom in, notice there's kind of a little, waves that are sort of in sync for a while and then they're out of sync. It's what we call a beat pattern. There's kind of a beat pattern here in the middle where something's going on. Those Frank Condon factors, there's like a series of peaks like that, and then there's another series that grows in like this. And then down here there's a third series that grows in like this. So we have 3 different series growing through our spectrum. And so we want to zoom in where that box is, and this is what we see. So this is the key. So you're looking for these 2 peaks right here that are equal. Notice it's high on the left on this side, and it's high on the right on this side, and here in the middle they're equal to each other. So you got high, low, almost equal, low, high. So that's the region. And so the one in the very middle of that is this peak right here. So you tell me the quantum numbers for that red dot, for that peak, using the key. So like if you find that wavelength, you write it in or copy and paste it into the table in Excel, and you're going to have a V prime column and a V double prime column. What do you put in the V prime column? So the V prime column is right here, these numbers. So V prime, this is 25, this is 20, so we're between 25 and 20. So let's go, so 20, 21, this is 22. So in the V prime column, that's 22. In the V double prime column, the V double prime column. So all of these blue numbers are V double prime equals 1. Yeah. So those the blue, all of that blue series, the V prime numbers are given by, 15, 20, 25, all of those numbers, and then all of those have a V double prime of 1. They're starting down here at the hot band, V double prime equals 1, and going up to 15, 16, 17, 18, 19, 20, 21, 22. So they're all starting in V double prime equals 1 and going to all those upper states. Okay. What about the one just next to it? This one here. So to the left, or the short wavelength side of that double peak, is right here. So the V prime column is 20 and the V double prime column is 0. Yeah, so then all of those in the orange ones are starting at 0, the ground vibrational state and the ground electronic state, and going to V prime, in this case 15, 16, 17, 18, 19, 20, 21, so on. It's hitting all of those up there in the top. And then all of these are different by that electronic energy difference that gets us over here into the visible region. This is the weird region, and I know, I mean, if I wasn't following this key, I wouldn't believe it either. Okay, so you just have to just go with what the key says. Here we have three series overlapping, and this peak 15 is really, really small. So it's like this little band head like this. Okay, and the blue one. Let's do the colors. Let me try that. It's going to slow me down, but let's try that. So I'm going to come over here. I'm going to get an orange color. Oh, I got to do this. This is going to be hard. Okay, come down here. Here's orange. Okay, so where's my pen? Okay, so for this, I'm going to draw for this little region right here. Oh my gosh, that was supposed to be a box. Okay, so there's a little orange peak like this, tiny, okay, and then let's do the blue one. Okay, then there's a big blue peak right here, okay, and then there's a red peak on top of that. And so when we add those three together, we get this little shape right here. We have a tiny little orange peak right here. Then we have a big blue peak, and then on top of that we have this tiniest little red peak. And that's what's happening right there when we have these three overlapping. So we have three different intensities, blue being the strongest peak in that region. And so all we're looking for is a sort of a change in, so it's coming up, you see a change in slope, and then it changes again. The slope changes again. Come on, pen. What happened? Okay. Okay. So the slope goes up, and then it changes again, and then it goes up again, and then it comes around the top, and then it changes again and comes down. So we see this little point right here, and we see this point right here. This one is easy to find, and then we see this one here, right here. So three places where the slope changes. That's the places we're picking. Like I said, only my mom would believe it, right? No, really, Mom, that's what it is. Okay, dear. Yeah, but I'm following what the guide was when I was doing this lab as well. I was like, okay, that's what they're doing. They're saying where the slope changes, that's where that band head begins, and so we're just going to pick that. So there's a little bit of artwork to be done here. Notice it's really only two places where we have all three overlapping. It's these two right here. Okay. And then it just goes to the twos and the ones. The zero is played out, and then we just have the two and the one. And again, we're looking at, like, notice up here, there's the funny little top of that peak, but the slope, like, it comes down again, and then it doesn't go down as steeply as possible. And then so there's that peak, and then here there's like a tiny little double at the top, And so we're picking the middle of that little double piece. So, but you can use your judgment, get in there and hover. So this is how we do it. We're going to get close to these. Well, let's see. First, okay. We'll revisit peak picking, but first we got to get the data into Excel. Okay, so you download it from Blackboard. I could have made a nice little Excel file, but I wanted to teach you guys how to do text to columns. You ever done that yet? Have you done text to columns where you bring the data in and it's all one column and you have to split it apart? Okay, so this is how you do it. You import this data into Excel. You want to create an XY scatter chart and expand the x-axis and so on and make those assignments. But this is how you bring it in. So you export this file into Excel. You can open it in Notepad and copy everything, go into Excel and paste it, first column, whatever, and you get one column of text. But the problem is down here, this is where your spectrum is, and notice that X and Y are all in the same cell. It looks like it's in the second cell, but it's not. You see the gray? That's where it's pasted. And so X and Y are in the same cell. We need to split Y out. So we have X and Y. So we need to take this text field and split it into columns. So this is a really important skill. So we can Control-Shift down to select the whole column. We go to the data ribbon, and there's the text to columns button. So we click text to columns, and we get this. And we have different ways of splitting that column. It could be a fixed width, which would be great. Sometimes the data is given to you where it's already in columns, but it's still just text, and Excel doesn't know where to cut the columns, and so you have to tell it. And a fixed width, you get to move the widths of those columns around until it gets the data that you want in each column. The other way is called delimited. And so there's a little limiter or delimiter that marks the divisions of the columns. How many people have heard of a CSV file? CSV is comma separated values. The comma is the delimiter. So that's what CSV means. It'll come in with commas between X and Y, and you have to tell Excel that the comma is the delimiter. In our data, the tab, it's tab spaced values. And so we have the X value, tab, Y value. And those columns have tabs in the middle. You just can't see that they're tabs. You just see a blank space. So you poke tab and see is it a space or a tab. You poke tab and all of a sudden you see this column divider pop up. And so that's telling you that it's splitting it on tabs. Okay, and then you can scroll down over here with the little scroll bar and see that the data looks good. When you scroll down over there, you see, yeah, we've got my X values in the first column, my Y values in the second column, and it looks great. Okay, and so then you've got your X and Y values. Yay! So X and Y for the spectrum. Select all of that and then do the scatter with straight lines. So we use this for spectra. As you know, y'all have plotted lots of spectra. Don't use the markers unless it's a small amount of data, and don't ever use the smooth lines. Why do I emphasize not using smooth lines? Well, yes. What were you going to say? Well, okay, so it's crazy, right? This smooth, but also if you draw a line on a graph as a scientist, you better know the equation of that line, because you're saying this is an infinitely resolved line, right? And so if it's a straight line, you can solve for that. You got 2 points and there's a line through any 2 points. And so you could tell me, even though you don't necessarily have it written down, if you have a spectrum, every data point's connected by a straight line, you could tell me the data point halfway between those 2 data points by using a linear fit. If it's a smooth line, you have no idea what that equation is. So don't use smooth lines. You could get in trouble. And plus, they don't always look good. Okay, and then for small data sets, you can use the markers. So if you click on that x-axis, you can zoom in, and this is what you get. So here's that region, what it looks like when you zoom in. And so here's how you get started. That's that V double prime equals 1, V prime equals 22, at wavelength 559.5. And so you would put those in your table and make this assignment table. And work your way, start here and work your way all the way. Don't just stop in that box that I showed. Go all the way until the peaks start to run into noise and in both directions. Okay. I had forgotten to say that one year, and all the students only picked those ones in that big orange box. And they left like 20 transitions unlabeled. And I was like, why did they do that? And I'm thinking, well, I guess I didn't ever tell them to. So go all the way till it runs out. Okay. We're doing minima on the short wavelength side. Use that guide to help you get started. Okay, so this is what you'll have as an assignment table, where you have all of your wavelengths. You'll convert them to wave number, okay, which is 10 to the 7th divided by wavelength. Okay. And then assign your V primes and V double primes, and you'll have the whole table assigned. And then you can do your regression. Okay. It's also nice to look for mistakes. You know, for the Rovibrational Lab, we had that V chart. They kind of had the J quantum number here and the R branch and the P branch, and you could see if there was a data point off of that branch. This Deslanders table can tell you if you've made mistakes too. It's a little strange to build, but this is the Deslanders table. So you have your V double prime quantum numbers. You have the 0, the 1, and the 2. And notice there's a skipped column in between them. Okay. And then you have the 0 to 14 transition is right here. So you paste in that wave number value there at 0 to 14. And then the 0 to 15 you paste next to that. Notice there's a skipped row in between. So that row is going to be the difference between the two. So this is the delta between those two. And so that's the vibrational difference in the upper level, because both of those came from V double prime equals 0. So between 14 and 15, that's the vibrational difference up here. And it should be close to the vibrational difference between 15 and 16, and it is. You see, if we go, the next one is 16, then this delta is also close to 100. So we have 99.7, 100.9, 95. The reason this table is useful is, let's say you paste one of your assignments in there and you get 200 instead of 100. You've messed up, you've skipped a line, or something's gone wrong, okay? So this table will help you discover errors. It's a pain to build, but it's a common tool. And so I would say, I want you to learn how to do it. Now, both of these hitting the 14 upstairs, okay? So this is hitting 14, this one's hitting 14, but they're starting at 0 and 1. So one starts at 0, one starts at 1. So the difference between those two is going to be the vibrational difference down here. So that's 210. So this is the delta between these two. And so we have 210.7, 210.2, 215. That's a little off, right? But then it's back down to 211. So I don't know that 215 is a mistake, but it is different than 210. And so we can look. Now, if you wanted the vibrational difference down here, you could average that column, right? And you've got the 0 to 1 vibrational difference. But you don't have to do that, because that's what the regression does. The regression analysis, the analysis of variance, gives us all of these averaged, all of the differences up here and all the differences down here, and gives you the best coefficient for all of them, and gives us your uncertainty. So you don't have to worry about averaging these columns or rows. And here's the Birch-Sponer plot. It's also a useful tool. It's kind of like that V plot for the P, Q, and R branches. But here you have the 0 transitions. We have the most of those because that has the most population. So the V double prime equals 0 has the most molecules in it, so we have stronger intensities. Then we have the 1 series, and you can see how it overlaps with the 0 series. It starts here and has a lot of overlap with the V double prime equals 1 series, 0 series. And then up here we see the 2 series come in, and it has some overlap with all 3. There's a few peaks where it overlaps with all 3, and then mostly overlapping with the 1. And so this is great. If you see a data point way off of here, you've made a misassignment. Okay, so then you can go explore that data point. Then we do the regression. So this is the results of the regression. I don't think I have this in your notes because I added it just at the end. I wanted you to kind of see the target that you're aiming for. Okay. Now we'll check your spreadsheet to make sure you didn't just take this off the video and type it in. Cut to the end, right? Cheat code. No, don't do that. We'll look and see if your data matches. But anyway, how did we do? Okay, we did pretty well. So 4 9s in the regression analysis. Not as good as the row vibrations because this assignment is much more difficult in terms of the V, finding those little spots where you're picking the peaks. It's much easier to pick peaks in the PQ and R branches or P and R branches for carbon monoxide. And so why is this one so big? This is one of the discussion questions. So everything is legit and statistically significant. This is the probability that noise in the data gave us this number. So noise in the data did not give us this number. It's a 1 in 10 to the 151st power. You'd win the Powerball like 10 times before random noise would give you that number in this data. But this one, we've got a 57% chance that scatter in the data give us this anharmonicity constant in the ground electronic state. So why is it so poorly determined? You could also look at the error. What's your value? 1.5. What's your uncertainty? 2.8. Right? So that's a reflection of this uncertainty. We're not confident in that number at all. Okay. What does anharmonicity tell me? How unequal the levels are. And look at the excited electronic state. It's very well determined because we have so many measurements of the excited electronic state. And we can tell, oh yeah, this one's a little smaller, this one's a little smaller, a little smaller, a little smaller. Down here we have 0 to 1. And then we have 1 to 2. And 1 to 2 is maybe a little smaller than 0 to 1, maybe not. And that's it. That's all we've got for the ground state. We've got 2 differences. And we're trying to determine if the second one is statistically different than the first. And we're just not sure. Does that make sense? We only have two difference measurements in the ground electronic state, which is the double primes. And so for the anharmonicity constant, we can't really say that the second difference is substantially different than the first difference. Okay. Here's and that's just basically what I was telling you right there with the potential energy surface diagram. And so here's our literature values. And then we have the derived values. So the equations in the handout would help you get the DE. And then we have the force constant here too. And so here's our absolute errors and our accuracy. And so you're able to compare. Some of these are really, really good. 0.91% error. Some are not so good, like the one we just looked at, 160% error. Oops. Okay. And then these unitless versions of X, if you wanted to calculate those are similar. And then our force constants look like they're both low by about 31%. So that's the Iodine Lab. I hope you enjoy it. It's a great one. And you'll share your the tedium with all of the PCHEM students that came before you and all the ones that come after you. So enjoy it. Bye.